Hey, I just wanted to quickly plug that if you guys want any tutoring, some new slots have opened. If you look in the description, there's a link to my physics and maths tutor profile in which I do tutoring on there. Hello everybody, welcome back to another episode of the A-Level Cookbook. Today we're going to be going through the OCR A-Level Chemistry A paper. This is the exact paper that I did actually when I did my A-Levels. I did OCR A-Level A Chemistry, I did AQA A-Level Biology, I did OCR B Physics, and then OCR A Maths, and my year was 2018. So it's going to be an interesting blast to the past. So a sample of boron contains these two isotopes, and the relative atomic mass of this boron sample is this. So relative atomic mass, remember, is just your abundance, your mass of whatever it is times each abundance plus all the other ones. So it could be percentages or it could be like, relatives, right? And it's over 100 or what the sum of all of these are. Now, in this case, let's say that the 10 has so the 10 isotope, there's X% of this. All the rest of it has to be 11. So all of it adds up to 100%, right? So the other 11 has to be 100 minus x. So therefore, its relative atomic mass is going to be 10.8 must equal 10x plus, and then 11 times 100 minus x, divided by 100. So if I times both sides by 100, I get 1080, and that will equal 10x plus 1100 minus 11x. If I tidy this up a little bit, I can get minus 20 equals minus x, and then x equals 20%, right? And it's saying how much of this is 11, so 100 minus 20 is 80%, so it's C. There you go. In this compound here, whatever, the oxidation state of chlorine is -1. What's the oxidation states of INSB in this compound? So they've told you that this is SbCl6 and it's a minus overall, right? Now they've told you that the oxidation number of chlorine is -1, so there's going to be -6. So something -6 is 1. -1, sorry. So it's going to be +5. So immediately that one's out, and then that one's out. So then we're stuck between A and C. So we need to have a look at this other one. So we've got ICl2. Now they've told you, and it's ICl2 plus, and they've told you the oxidation of chlorine is that. So -2, something -2 gives you 1. So the only thing that it can be is 3. So there you go, that one's out, so it's C. Next it says, what's the number of hydrogen atoms in this? So if we look at how we've got 0.125 moles of C2H5OH, right? In this thing, there are 6 H's. So if there's 1 mole of this has 6 of these in them, then we're going to have 6. So the number of H's, moles of H, sorry, is going to be 0.125 times 6. Because if you think about it, imagine I have a square, right? I have one square and it's got 1, 2, 3 triangles attached to it. So 1 square plus triangles. If I then divvy it up, I've actually got 3 triangles and 1 square, don't I? As a whole unit, it's this. So in this scenario, if I had 2 of these, I've got 2 square plus triangle, but I've actually got 6 and then 2 of these. And that's what's going on here. We have 0.125 of this whole thing, but there's 6 in each one of these. So we actually have 6 of this within the unit if you break it down into its chunks. So here, that's how many moles of this we have, which is going to be 0.75 moles, right? But they want to know the number of hydrogen atoms. This is moles. Moles are just multiples of Avogadro's constant. 1 mole is 6.02 times 10 to the 23. So if I have 1 mole of a banana, I've got 6.02 times 23 moles. Sorry, bananas. So here what we need to do is 0.75 times Avogadro's constant, and that'll tell us the actual number. So if we do that, we get 4.515 times 10 to the 23, which is B. There you go. So now it says a student titrates a standard solution of barium hydroxide and nitric acid, and this much was needed to neutralize this much. What is the concentration of the nitric acid? So we need to use, we're looking for the concentration, we need to find out the moles, right? So then just quickly sketch out what's happening here. So BaOH2 plus some H, blah, 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 plus HNO3s, right? It's going to make whatever. This is a 2 plus, that's a 1 minus, and there's also BaOH2, right? So we're going to need 2 moles for every one of this. So the moles of the BaOH, blah, 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 whatever, right, is going to be its concentration times its volume. So volume is 125 over 1,000 times its concentration, which is 0.045. If I do that, I get 1.125 times 10 to the minus 3. So I know that this takes 1 mole of this requires 2 moles of the acid, right? So then the moles of the acid, blah, 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 is going to be like that times 2. So I know that the moles of this is going to be 2.25 times 10 to the minus 3. The question's asking what the concentration of the nitric acid is, right? So we're going to use the volume of that nitric acid. So C equals N over V, which is going to be 2.25 times 10 to the minus 3 divided by its volume, which is 23.35 divided by 1,000. If we do that, we get roughly 0.09635, blah, 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 which is D. Which statement explains why nitrogen has a larger first ionization energy than oxygen? So compare them side by side and see what's up. So if we do that, we get, let's have a look. So there's a quick shortcut you can take. Sorry, I've cropped off the rest of the P block, right? Period 1, period 2, whatever, period 3, right? We're looking at nitrogen and oxygen. So that's going to be 1, 2, 3, 4. So it's going to be 2p3, 2p4. Now, instead of trying to memorize and whatever, right, you can just kind of logically work it out. If you're doing the first ionization energy, you are pulling out an electron from here and here. So you're doing it from 2p3 versus 2p4. The only difference between 2p3 and 2p4 is that you have, 3 electrons versus 4. However, here, let's have a look at our p orbitals if we actually divvy it up like this. So 1, 2, 3, they fill up singly, remember, and then the other one it's 1, 2, 3, and then 4, right? For some reason, this requires more energy than oxygen to take out. So the only difference between these two is that these are singly filled and this one has a double filled one, and it's actually from there. So the reason must be is one of these, n atoms of left repulsion between p orbital electrons and O. I mean, that's objectively true. There's one shared pair, one singular in each, and then there's a double there, so that's true. They have a smaller nuclear charge. No, not really. It's the other way around. They lose an electron from the 2s subshell. Nope, that's incorrect. They have an odd number of electrons, and that's not correct either. It's all to do with what you're peeling it out from in the outer orbitals. It's A. So you just kind of work it out like that. I mean, it obviously makes sense. These repel. So in the periodic table, X is in group 2 and element Y is in group 15. What is the likely formula of this? If it's in group 2, you're going to have X, 2 plus, and then if it's 15, it's going to be like Y 3 minus, for example, right? So it's whatever fits the bill here. So that's got to be, for example, to match their numbers, you would do times by 3 times by 2. So you'd have X3Y2, which is C. So which statement about ammonium carbonate is not correct? So it reacts with barium nitrate to form a white precipitate. That is true. Carbonates tend to form white precipitate, so that one's out. And then if we have a look at the next one, it says FFSs would dilute nitric acid. That is correct because it's a carbonate, so that's out. It releases an alkaline gas at warm NaOH. It will do because it's got ammonium in it, so it's got to be D, which is indeed correct because it's CO3 2 minus, but this whole NH4 is NH4 plus, so we actually need 2 of them, so 7 is D. A reaction is first order with respect to reactant X, which rate concentration. So you've got rate and concentration here. Graph is this correct shape. So if it's first order, what it means is that the rate is proportional to the concentration of X, meaning that if you double this doubles as well. So if we're looking at rate and concentration, each step it should increase by the same amount, right? So from here to here, that's like how much it's gone up by. But if we take that same distance, it's gone up by the same slope, the same straightness, the same slope. And also, if that's 0, that's 0. It's gone straight through the origin, and it's increasing with concentration, so it's got to be A. It's proportional. It's a straight line. If it's proportional to itself and not squared or anything, it's a straight line through the origin. So that's there. This one, the rate's going down with the concentration, so that's incorrect. Here, the rate is not changing at all with concentration, that's incorrect. And this one, it's shooting up exponentially. So it could be second or third order because it's proportional to its squared. So that's out. The reversible reaction of sulfur dioxide and oxygen forms sulfur trioxide. An equilibrium mixture contains these, and the pressure is that was the partial pressure of SO3. So the total moles is going to equal those all added up. So that's 2.4 plus 1.2 plus 0.4, which gives you 4 moles, right? And then we need partial pressure equals the mole fraction times the total pressure, right? So the total pressure they've told you is this. We need to work out the mole fraction of the SO3. So the SO3's mole fraction is 0.4 over 4, so then its partial pressure is going to be 0.4 divided by 4 times the total pressure, 50, and if we do that, we should get, 25, so that means it's B. A buffer solution is prepared by mixing this much propanoic acid and this much sodium propanoate. What is the pH of this buffer? So, real quick, every time I do an acids-base question, I always just write HA plus OH minus makes A minus plus H2O, right? And then I'll do an initial and then an end. Because usually I do questions where it's a weak acid plus a base, and then you get this and that, right? So a buffer is always made of a weak acid mixed with its salt. In this case, they've mixed this much propanoic acid with this much that. So we need to quickly work out the moles of everything going on here. So the moles of the propanoic acid is going to be 200 over 1,000 times 2, which is going to be 0.4 moles. There's no base added, so that could be 0. And the A minus is 600 times 10 to the minus 3 times 1, which is 0.6. These are not going to react. It's all done and dusted. The reason I write like this is because then I can see visually that they've added a base and those two would react, so there's got to be an end as well. So at the end, it's also 0.4 and 0.6. Now, we need to decide which Ka formula we're going to use. It's going to be H plus and A minus. It's not the H plus squared one because the A minus is the salt. In normal weak acid, if it's a weak acid on its own, because the dissociation is so far to the left, you have barely any of these two, so they're kind of equal, that's why. So in this case, whenever you see an H plus A minus into buffer, it's a salt that's there. So then we need to work out these new concentrations in order to actually use this, so then the new concentrations are going to be 0.4 over the new volume, which is going to be what? 200 plus 600, so it's 800 divided by 1,000, and you're going to divide 0.4 by that. So if we do that, we get the new concentration is 0.5 for you, for the HA, and then for the A minus, it's going to be 0.6 divided by that, which is going to be 0.75. Alright, now they want the pH, so we're going to have to find H plus. So KaHA over A minus equals H plus, right? So that's going to be this times what we just did, all of that stuff, right? So it's going to be 1.32 times 10 to the minus 5 times our HA, which we just worked out as 0.5 over our main A minus, which is 0.7, right? So that gives you 9.4 times 10 to the minus 6. If we pH negative log to the base 10 of that, we get an answer 5.06, which is C. There you go. So here's some standard entropys. What's the entropy change? So delta S is the S end minus S start. It's going to be S end, the entropy at the end, which is 1 mole of this. It's going to be 239.7. And it's going to be minus the start, which is going to be 197.6, plus 2 lots of the 130.6, because there's 2 moles of it in that. So if we do that, we end up getting, we get minus 219.1, which is A. So there you go. And make sure you just be careful with keeping an SN start, otherwise you'll get the other sign instead, the wrong way around. The redox equilibrium for a hydrogen oxygen fuel cell and alkaline solution is shown here, so shown below. What's the overall equation? So whichever one's more negative is the one that's getting oxidized, and whichever one's more positive is the one that's getting reduced, which means that if this one's getting oxidized, it's going this way. If this one's getting reduced, it's going that way. So what means is we're going to have this plus this plus this plus this gives you this and this, and like, you know, all sort of mishmashed up and balanced out. So if we do that, we get H2 plus 2OH minus plus a half O2 plus H2O goes to 2H2OL plus OH minus, right? But then you can see these cancel out. Sorry, 2 OHs, that cancels out. One of them cancels out, so we're left with just this, that goes. So you're left with H2 plus a half O2 gives you H2O, which is exactly what the overall equation is. So it's just D. That's actually a free mark if you just remember that hydrogen fuel cells all share that sort of overall thing. But you can just quickly work it out if in doubt. Then it says, which enthalpy changes are endothermic? So endothermic means you're putting energy into something. So it's usually when you're breaking a bond, you've got to put energy in. So that's why it's bond breaking. Exothermic's energy is released. So it's the opposite, so it's going to be bond making, right? So which one of these are endothermic? So number one, bond enthalpy is the mean bond, the mean energy required to break 1 mole of a blah 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 bond, whatever, right? So immediately that's one of them. Then if we look at the other ones, we've got second electron affinity of oxygen. So your first electron affinity is exothermic because you're making bonds between you know, the electron and this the atom, because of attraction to the nucleus and so forth, right? The thing though is that when you've got a negative ion, you're now repelling. Because you've got O minus, if you want to add an electron to it, you're actually repelling that electron away. So you've got to put energy in to force it to join. So that means this one's also endothermic. The second electron affinities are endothermic because you're again having to overcome that repulsion to actually get it to get there. So that means it's this. And then standard enthalpy of formation. Well, formation is where you're making bonds, and making bonds is exothermic, so it can only be 1 and 2, which is B. Which statements explain why reaction rates increase as temperature increases? So every single reaction in the entire universe hinges on 2 things. The 2 things it hinges on is collisions in the right orientation and so forth, but also having the activation energy. So whichever ones max out these is what's going to give you the answers. So in this case, it's not the activation energy less, that's a catalyst, that's out. Collisions are more frequent, that is correct because of more kinetic energy, and the greater proportion of the energy that's required for activation energy, that is also correct, because if you draw your Maxwell Boltzmann distribution, whatever, right? Very rushed. Here's your activation energy. If you increase the temperature, it skews it like that, so there's more way above the activation energy. So in that case, that's what it is. Catalysts is the only thing that reduce the activation energies. It's just more of them have enough, so that means it is C. It says, which statements are correct for this complex that's square planar? So one of its stereoisomers is used as an anti-cancer drug. That is indeed correct. It's cisplatin in there. Its bond angle is not that, and it's not got 2 optical isomers either. So it's optical isomers is when you've got a bidentate ligand against a hexa, you've got an octahedral complex with bidentate ligands, so 6 coordinate bonds, and its bond angles for this is tetrahedral, not square planar. So that's out. So this question is about enthalpy changes. Here's the enthalpy changes that can be used to determine the enthalpy of hydration of fluoride ions. So we've got hydration, solution, lattice enthalpy. Fine. It says, explain what is meant by the enthalpy change of hydration. You really need to know your enthalpy definitions, what you start and finish with, and what states you're changing from and to, because all of this hinges on you knowing those definitions and how to turn them into equations. If you're complaining about having to learn these definitions, you've heard me say this again and again and again, you don't know what you're doing, and you are absolutely fumbling this topic horrendously. Don't memorize cycles, use your common sense and think about it. Like, be able to turn an equation into a sentence and vice versa. So if it's saying enthalpy of hydration, that is the enthalpy change when 1 mole of aqueous ions are produced when gaseous ions, 1 mole gaseous ions dissolve in water. Right? That's that. It says the enthalpy change of hydration can be determined using the enthalpy changes in this table. On the dotted lines are the species present, including their state symbols. This is all about Hess's law, but just like big. That's what Born-Haber cycle is. So all of these arrows are enthalpy changes. So we need to know your definitions to be able to actually make use of them. If you're doing hydration, you're going from gaseous calcium to aqueous calcium ions. So that means you're going to start with G and you're going to go aqueous, right? Solution is where you dissolve 1 mole of a solid ionic compound, blah, 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 and whatever, and then you get Ca2 plus aqueous and 2F minus aqueous. Lattice enthalpy is when you make 1 mole of a solid ionic compound from its gaseous. So you're going to have Ca2 plus gas plus 2F minus gas goes to Ca F2. That's why these are important, because then it helps you put them in the dang cycle. Or sometimes you might have to make your own cycle. So lattice enthalpy, you know you're going from gaseous ions to a solid ionic compound. So it's going to be Ca2 plus gas plus 2F minus gas. Then, for some reason, you can do that, and then you can go back up this way. So you need to figure out what that could be. So at the very bottom, I know I'm going to make a solid ionic compound, CaF2, solid. Now, for some reason, I can go back up here, and I can also go around all the way around this and get to the same point. So it must be that I'm hydrating both of these to eventually get down to the enthalpy of solution. So I can do the enthalpy of hydration is the Ca2 plus, and then 2F minus stays as a gas, and then I'm enthalpy hydrationing the other one, so Ca2 aqueous, 2 plus, and then 2F minus aqueous. There you go. Like that. You need to know those definitions, otherwise you are just fumbling like, nah, like, you know, just don't. Then it says calculate the enthalpy change of hydration for the fluoride ions. Each arrow is an enthalpy change. Just look at it. So you've got lattice enthalpy this way, right? Right, and then we've got like our, you know, from here to this, that's enthalpy of solution. This is hydration of fluoride. This is this, right? So just put the numbers on the cycle and use it. And you should draw Hess's law cycles in any of these by determining what these actually mean, what they turn into, and then making your own. Don't memorize cycles. I think that's pointless. So here, minus 2, 6, 3, 0. This arrow is the enthalpy of solution, so plus 13. What else have we got? We've got the hydration of Ca2+, so that's going to be minus 1609. This is the mysterious one here we want to look for, but the enthalpy, the hydration definition says well, it's 1 mole of aqueous ions made from gaseous ions. There's 2 here, so it's going to be 2x. So then, if I start and finish at the same point, no matter what route I take, it is the same. So if I start here, and I go all the way to here, so if I start here and finish here, this route is the same as this route. So then I can say that the minus 2360 plus the 13, so minus 2630 plus 13, equals, because I'm going to start here and finish here, it's going to equal these two steps going down. So it's going to be minus 1609 plus 2x. Then I'm going to tidy this up, which gives me minus 2617 equals minus 1609 plus 2x, and then I'll get minus 1008 equals 2x, which then means x is minus 504 kilojoules per mole. There you go. Then it says predict how the enthalpy changes of hydration and of F minus and Cl minus would be different. So F minus versus Cl minus. Have a think what the difference is. This is down one in the group, so it's bigger, right? So then, if that's the case, what do you think that could do with the hydration? So you need to think about the interactions with these things between other stuff. So right, if you've got this F minus ion, it's going to polarize the water and all that stuff and form bonds with it. So if this is a bigger one, you've got that positive nucleus there, and you've got the outermost electron further away and so forth, right? That means it's going to form weaker bonds than this. If it's making stronger bonds, as in more energy is being released when they're being made, it's more exothermic, so that's what it's got to be. So F minus has got to be more exothermic. Why? Is because it's releasing more energy, and the reason why is because F minus is smaller than Cl minus, so that means there's going to be more attraction to the water. So rather than memorizing it, I can just kind of work it out like that, because the only difference between these two is the size. Now it says the fluorine reacts with steam in this, and it says the average bond enthalpies are here, and then it says what is average bond enthalpy? So it is the it's the average enthalpy change when you break 1 mole of bonds in gaseous molecules, right? That's what it is. It says calculate the bond enthalpy of this, right? So whenever you're doing this, you must draw a cycle. I don't want to hear none of that like, oh, bonds are made, bonds broken, rubbish, right? Write the overall equation again and what you know. Draw Hess's law cycle. Every arrow is an enthalpy change. So 2F2 plus 2H2O goes to O2 plus 4HF. Do it this one, you'll never get it wrong. Delta H is going to equal minus 598 for this reaction. The bond enthalpy is when you're breaking this. So it's going from a 1 mole bond to atoms. So look at this and then look at this and see what you've got. Obviously, we've got more than 1 mole. So this is bond and bond, where enthalpy, you know, whatever. This is made of these, right? So it's going to be broken. These this O2 is made of this. It's going to be broken. This is made of this. It's going to be broken. So we've all of these at the left-hand side of this, and all at the bottom is probably got to be the atoms, right? So my bottommost side, I'm going to be lazy and write that. So then if I'm bond enthalpying this, right, I'm breaking the FF bond. In FF, there's one of them, right? But they've got 2 moles of this, and the definition says when you're breaking 1 mole, so I'm going to have 2x. Then, if we look at the 2H2O, H2O has 2 of these, right? Because if you draw it real quick, you do that. And then you've also got 2 more, so there's actually 4 lots of the 464, because there's double that. So 4, 6, cool. then the arrow goes down from there to there because you're bond enthalpying it, which means you're breaking that 1 mole of bonds into atoms, right? It's not going up or anything, it's going down because the definition says you're breaking this into its bonds. So that means it's 1 mole of it, and there's only O and O, so it's 498, and then here, again, same thing, HF, so it's going to be 4 lots of 568. So that Hess's law says if you start and finish at the same point, the enthalpy change will equal the other route you go around to get from the start to the finish. So that means we can say that minus 598, the overall enthalpy change here, is equal to this route and then back up. So 2x, because I've followed the arrow, plus 4 lots of 464. Then we're going against this arrow, so minus 498 minus 4 lots of 568. So then if I just tidy this up, I get minus 598 equals 2x minus 914. So then if I could then get 2x equals plus 316, because remember its enthalpy changes, you only keep the plus in, so x is going to be half of that, which is plus 158. If you do it this way, you'll never, ever, ever, ever get it wrong. I don't want to see no bonds made, bonds broken rubbish, man. This is how you do it. Unless you put the numbers wrong in your calculator or, like, I don't know, decide to be like, oh, the arrows go this way by not even looking at the definition and just kind of using your head and guessing. So this question is about reaction rates. Aqueous ions Fe3+ can react with this as shown below. Student carries out the experiment to determine how the different concentrations affect the initial rate, and the results are shown. It says determine the rate constant and then determine the rate constant and then determine a two-step mechanism for reaction that's consistent with this results. So what we're going to do is we're going to work out the orders first by comparing them. So if we look at the orders, let's have a look what's going on. So between experiments, what have we got going on? So from here to here, we're doubling this, and that's staying the same. So between experiments 1 and 2, Fe3+'s concentration has been times by 2. What happens to the rate? The rate gets times by, so you would do 1.62 times 10 to the minus 3 divided by 8.1 times 10 to the minus 4, which has also gone up by 2. So therefore, the order with respect to Fe3+ is first order. Cool. Then let's look at where we change this. So between here, it's between 2 and 3, but this also changes too. So then let's have a look. So experiment 2 and 3. What happens to Fe3+? The Fe3+ has been times by a half, because we're dividing it by 2. It's always easier to do it in times's, then it kind of helps you picture it a bit better. And here we're doubling the I. So I minus has been times by 2. So then this has gone up or changed or whatever. The rate, that means a half times 2, right, has led to the rate doubling. So it's a half times some mysterious 2 to the x. So if I do a half to the rate, then the rate should have halved, right? So then if I undo the half, then if I do 2 to the x, that means this rate has gone up by 4. So that means that it's 2 squared, so this means it's second order. Another way to think of it is that I've halved this, so surely the rate's halved. But then I've also doubled this, and the rate's gone up by 2, which means the 2 has been halved, which means it's 4, so that means the order with respect to I minus is second order. Then it says determine the rate constant. So we actually need to work out this is. So R equals K times I minus squared Fe3+. And then we can just work out K by doing K equals R over the whatever we want to pick. So we're going to choose, I'll just do this last one. So 3.24 times 10 to the minus 3 all over the concentration of the iodide, which is 6 times 10 to the minus 2 squared. And then the other one, which, and also, does it want the units as well? And it does want the units. Yes, it does. We'll get to that in a sec. So if we do that, we get 22.5. If we just look at the units, so rates are always in moles per decimeter cubed, so x to the minus 1. We're doing moles dm minus 3 squared, mole dm minus the power of 1. So then that becomes mole dm minus 3s minus 1 all over this whole thing cubed. So it's going to be moles. So that's like saying mole to the 1, mole to the 1. But if we're cubing that whole thing, it's going to be mole 3 dm minus 3. It's going to be minus, so it's minus 3 cubed. In this context, it's going to be minus 9. So then, that's like saying 1 minus 3. So it's going to be mole minus 2 dm, and then what's that? Minus 3 minus minus 9, 6 s to the minus 1. There you go. So you've done the first part, determine the rate constant. It says it's a possible two-step mechanism. So when you're doing a two-step mechanism, it's got to overall result in this. So if I just write our overall equation just down here, so it's going to be 2Fe2 plus 2I minus goes to 2Fe2 plus I2. So whatever steps these mechanisms have got to be, it has to start with this and finish this overall. We can make some weird in-between stuff as long as they disappear. So then if I know that these two are here, I know my slow step, the rate determining step, the step that's as fastest this thing can go, is going to be what's in here, and these are going to be the moles of it. So I can say off the bat that our slow step could be Fe3 plus 2i minus aqueous. So slow step 1. And the other one is going to be step 2, and that's fast. This step 2 can't have either of these in them. So you can see that we're starting with this overall equation has 2, but this rate equation only has 1. So you can only put 1 here, so we still have an extra Fe left. That's been dealt with in this step, right? So on this other step, I must have the other Fe3 plus as the other reagent. That means I've got that left, right? So whatever this is this plus something makes something. Now, that means we're going to have to eventually make this somehow. So Fe3 plus was 2i minus. Maybe I could make... Maybe I could make Fe plus aqueous and I2, like liquid or whatever. Or, yeah, like liquid, yep. So in that case, then I could do Fe3 plus and Fe plus aqueous makes 2 Fe2 plus. There you go, that satisfies that, because then you got this and this. It's kind of just mishmashing them until you get what you need, as long as there's some reasonable, feasible possibility. Because here, I'm saying that this has become Fe2+, so that's been reduced, but not all the way, and then this gets oxidized while this gets reduced, and then you get this happy thing here. All of their alternatives are like, for example, making FeI2+ as a whole complex and stuff. You can just have a look at the mark scheme. But basically, it's just eventually coming out with some weird intermediate that disappears, so you're left with this and this. So in the first... you just need to make sure that each step eventually has all of these so that they're gone, and then eventually they all make this and nothing else, and you're happy with that. There you go. A student carries out an investigation to find the activation energy and the pre-exponential factor A, and they plot this graph here, draw a straight line best fit, and calculate the activation energy. So if I just do that now, this is horrendous because it's hard to do on my tablet, so just pretend that's like perfect, right? So then it says here to what? To work out the activation energy in joules per mole. So look at the formula first and then look at graphs. Every single straight line graph in the universe follows y equals mx plus c, right? Well, y is your y-axis, this is your gradient, that's your x-axis, that's your c. So this formula they've given us is ln k equals, minus ea over rt plus ln a. That's the formula we have. Compare it side by side. Y has been replaced with ln k. So that means we have ln k equals, look at the x-axis, that's 1 over t times 10 to the minus 3, right? So now we've got 1 over t, m times 1 over t plus c. Compare it to this top part now. If you look here, that's 1 over t times that. So m has to be minus ea over r. The gradient has to be that. And then c has to be ln a. So there you go. Now you know what the gradient is. So the gradient is minus ea over r, which is going to be y2 minus y1 over x2 minus x1. So what you do is you just pick two coordinates and do them. So if I do that, if I pick two nice coordinates and I'm rushing this, I'm going to go with... There's my first one. And then we'll go with you, right? So the next thing though is that people always, I've seen a bunch of people do this as their y2 and then that as their y1. That's wrong. This is your y2, that's your y1, because you read graphs from left to right. If you do that, you would get a positive result, which would suggest that the line's going up as a positive gradient. Here it's negative, it's going down. So always do your furthest right one as your y2 and then your left one as your y1 and so forth, right? So here, this is going to be, if I read this off now, our y2 is going to be... Whoops. Oh, nice one. It's just died. It's going to be 28.9 minus then y1, which is 31.3. Not the other way around, and you'll get a falsely positive wrong result. Over 3, but it's times 10 to the minus 3. Be careful. So that's 3 times 10 to the minus 3 minus 0. If I work that out, I get a gradient of minus 733.333, right? That's minus EA over R. So then minus EA would be 8.31 times that. So sorry, 8.314, sorry, times that. Which if you get that, minus EA equals 14. You get... So activation energy, they want in joules per mole anyway, so it's 6096. Now, I've read this horrendously and rushed through it. So like, if I probably took more time, I'd probably get a more accurate result. And like if I drew the line properly, because my pen is rubbish and this tablet's not so good. So the range they accept in the mark scheme is 6650 and 8650, but the technique's the same. Then it says use the graph to work out the pre-exponential factor A. We've just set up here, C is ln A, the y-intercept. So ln A is going to be what our y-intercept is, which is what, 31.2. So then, again, I've read it horrendously. In the mark scheme it says 31.8, but I'm doing 31.2. So to undo ln, you just do e to whatever the ln value is. So e to the ln something will give you... like, you know, the x. So to undo an ln value, all you do is you just do e to the power of that thing, so 31.2, and it'll give you what you want. So if I do that, I get e to the 31.2, which gives me 3.5 times 10 to the 13. But again, I've read it horrendously, and my graph is rubbish, so you just need to do it properly, and yeah. But whenever you have ln a, that's the same as saying log to the base e of something. So you know how you do like log to the base 10, negative log 10 h plus, right? And you do 10 to the minus... Sorry, you do 10 to the minus whatever, the pH value to get your H plus again. same thing here. You're just doing e to the whatever that thing is. So e to the whatever this equals, your log value, your ln value, and it will give you the original thing. Similar thing here. There you go. So nitrogen monoxide reactor form this in this reversible reaction here. It says write an expression for Kc, so it's going to be NO2 squared over and concentration of NO squared O2. You don't want to be misled by the fact that it says gas, because these are concentrations. It's Kc there. So then units wise, that's going to be mol dm minus 3 all squared all over mol dm minus 3 all cubed, because we're doing that squared times that, right? So then that becomes mol dm minus 3 to the power of minus 1. So that means you're going to end up with mol minus 1 dm 6, because that's like saying mol minus 1, right? But if you're doing it like this, then it's going to be that times that, rather than adding. So there you go. It could be mol minus 1 dm 3. Cool. A chemist mixes together this and pressurizes it so the total volume is that. The mixture is allowed to reach equilibrium at constant temperature and volume. The extra equilibrium mixture contains this. And then under these conditions, this is that. We find out the amount of moles in this equilibrium mixture. So always rule number 1 is to look at the question and use the reading comprehension skills. That does not mean you have immediately this. You do reaction stoichiometry. That's not how this stuff works. When you're mixing these two together, this is going to go down, this is going to go down, that's going to go up. So we need to figure out by how much everything's gone down / up. So what you do is you write the entire thing again here, down, here, like this. And then what you do is you work out your initial moles before equilibrium, then your change, and then your final moles at equilibrium, in this case, when equilibrium is reached, and then whatever you need as well. So we're going to probably need a concentration possibly, right? The question told you that they mix nitrogen oxide and pressurize it, so this total volume is that, right? And it says they've allowed it to reach equilibrium at constant temperature and volume, and under this it has this much at equilibrium. So the amount of equilibrium we have here is 0.40, and then this is 0.80. Fine. So if this is this must have changed by something, this must have changed by something, and then this must have gone up by something to give you X. We need to find the concentrations at the end. So they've told you that the volume of this is 4 deciliters cubed. So the concentration in this is going to be 0.40 over 4, and then this is going to be 0.80 over 4, and that's going to be X over 4. We don't know what it is. So then that means a concentration at this is going to be 0.1, and that's going to be 0.2. Now they've told you that Kc is 45, and we know that Kc, which is now 45, equals NO2 squared, which is going to be X over 4 squared, over the NO squared, right? So where are you? That's going to be 0.1 squared times 0.2. So if I tidy that up, I get 45 equals X over 4 squared, all over 2 times 10 to the minus 3. So then if I times both sides by that, if I do that times 45, I get 0.09 equals X over 4 squared. If I square root that, then I'll get 0.3 equals X over 4. So then if I times that by 4, I'll get my final answer of X equals 1.2 moles. There you go. Because I've that goes back to moles, because this is its volume, remember, and I've times it out by its volume again eventually. So it's just moles, that's it. And also that's the X here as well, so you know it's that. So the value of Kp at 298,000 Kelvin is shown below. So then it says here's the temperature, here's that, right? So let's have a look what's happening. So here you can see that the temperature is like lower, but so lower temperature but higher Kp. Here they've increased the temperature, we get lower Kp. So Chatellier's principle says that if you make a change to an equilibrium, the equilibrium can be shifted to counteract the change. So if I look here, for example, if I increase the temperature, the equilibrium wants to counteract the change, which is to decrease the temperature. By doing that, for some reason, whichever way it's gone has made Kp lower. Now Kp is obviously going to be your products over your reactants, which means it's shifted that way. So if I've increased the temperature and it's shifting to the left, then that means that this forward reaction has to be exothermic. Why? Because Kp decreases as temperature increases. The chemist increases the pressure of this equilibrium. To suggest and explain in terms of Kp, what would you expect to happen to the equilibrium change? The temperature's changed. Chatelier's principle says, well, to counteract the change, so they increase the pressure, so the equilibrium will shift to decrease the pressure. And it does this by, because I always like doing it like this, because then I'm always getting all the points. I'm saying the change was this, it wants to do this, and it actually does it by shifting either left or right, right? So if it's going to lower the pressure, it's going to move to the side with fewer moles, it's going to go right. So it moves to right to side with fewer moles. So then Kp product increases, but the reactants decrease. And what this does is this restores Kp to normal though, because everything's sort of balancing back out again. So Kp's number doesn't actually change. No change in Kp number, because only temperature changes this. That's it. The only factor that affects Kp is temperature. Otherwise, as this goes up, these will just go down and it will all balance out. So it's like, you know, the only thing that does that is temperature that changes it. For every Kp, Kc, Ka, anything. This question's about acid and base found in the home. Ethanoic acid is the acid present in this vinegar, and they do an experiment to find the pKa of this, the concentration of this is this, and the pH is that. So write the expression for the dissociation constant of this. So Ka equals H plus CH3COO minus over CH3COOH. Like that. Now it says to calculate the pKa value of this. So we need to find out what Ka is. Now here, your two options are to use the H plus and the A minus over HA, right? But in this circumstance, it's only acid on its own. This is only present, A minus equals salt when you're using a weak acid, because the dissociation is so far to the left, these two are practically equal. Right, so whenever you have an A minus in this, it's because there's a salt in there, which means when you have a weak acid mixed with its own salt, you have a buffer. So Ka equals, in this case, H plus squared over HA instead. So if I want to work that out, it's just going to be the H plus squared. They've told you the pH, which is going to, so the H plus is going to be 10 to the minus 2.41 squared over its concentration of 0.870. So if I do that, I end up getting 1.739 times 10 to the minus 5. So if I negative log to the base 10 of this, that'll give me pK, because the P just means that. So if I do that, negative log to the base 10 of that, I get 4.76. There you go. Now it says determine the percentage dissociation of ethanoic acid and vinegar, and then give your answer to 3 significant figures. So what it's saying is that if we think of it this way, so HA becomes H plus and A minus. So the percentage of its dissociation is going to be this over the original thing that it becomes, right? It's going to be H plus over its HA times 100. We could use A minus, but they're both equal. So we're just looking at how much it's dissociating by. So in that case, it's going to be its concentration, which is going to be 10 to the whatever it was, 10 to the minus 2.41 over the concentration that it's at, which is 0.870 times 100, which if you do that, you get 0.447. There you go. Many drain solid cleaners are based on this NaOH, so what they did is they got, and please read the question and just carefully use your logic here. So they've dissolved this drain cleaner and made up a solution of 100 centimeters cubed, right? That's going to have NaOHs in it, and they're going to dissociate into H's and OH minuses, right? And they said that they got this pH of this. Determine by mass the amount of NaOH. So we need to think about pH here. pH is linked to H+, right? You need to think, what do I know links H+ and OH minus? It's Kw. Kw equals H+ times OH minus. Now when it's pure water, these two are equal, but we've just now slapped a whole bunch of NaOH in there, so that's going to mess things up. And that's going to make it change. So then if the H plus is 10 to the minus 13.48, we can find the OH minus, which must have all come from this, which must have all come from this. So then Kw over H plus will give you our concentration of OH minus, which is going to be 1 times 10 to the minus 14 over 10 to the minus 13.48. If I do that, I get, this is 0.302 moles per decimeter cubed. So that means that our all of that must have come from the NaOH, because it would dissociate into Na plus and OH minus, right? So the concentration of the NaOH has got to be 0.302 mole cubed. Now we know the moles equals N equals CV. We know its volume is 100, so it's going to be 0.302 times 100 over 1,000, which means you're going to get a moles of that, which is 0.03019, and that's moles. We can work out the mass now because we want to find out how much sodium mass is in this thing. So we're going to do moles times MR, which is going to be your answer, times the 40.0, which is the mass of the NaOH, which gives you 1.21 grams. Then what you do is 1.21 over 1.26 times 100 to give you a percentage, which is 95.9, because it's 3 significant figures. Done! Next it says sodium carbonate is used in washing soda. It contains the carbonate ion as shown below. Draw the dot and cross diagram for this carbonate ion, show the outer electrons, and use different symbols for electrons and any outer extra electrons. So fine. What I usually do is I draw my carbon atom, and I'm going to draw the outermost electrons. I know it's in group 4, and I can see there's some single bonds here, so I'm going to draw a nice X here, a nice X here, and then like an X here, and then an X here. Because I know there's a double bond, there's going to be two shared pair of electrons. So oxygen here is sharing 2, so it's going to be this on that side, right? And then it's going to have the rest of the oxygen. So 1, 2, 3, 4, 5, 6, 7, 8. Nice. And then on this side, these are single bonds. So there's going to be a single bond there. So the electrons in the oxygen, remember it's in group 6, it's given 1 there. So 2, 3, 4, 5, 6. Right, 1, 2, 3, 4, 5, 6, 7 though. But you can see it's O minus. It's got an extra electron, so you put another symbol there to show that extra electron, and that's what's giving it 8. The same thing here as well. So O, 1, 2, 3, 4, and then 8. So that's what's giving it the minus, otherwise it wouldn't be minus. And then as well as that, sorry, we should really draw the 2 minus there as well. So this question's about the halogen groups and elements, and it shows the transitive properties, and it shows the boiling points down the groups, and explain why they show this. Compare them side by side, right? As you go down the group, for some reason, this boiling point is getting higher. So then when we're boiling it, for example, Cl2, we're not breaking this. That's the covalent bond, and that would be Cl and Cl. That's wrong. We're breaking these forces that are holding these molecules close together, and those are called intermolecular forces, between molecules forces. So look at all of these and compare them. When you're boiling them, you're breaking these intermolecular forces. So then, the intermolecular forces here are just going to be London forces or van der Waals or induced dipole-dipole. And actually, it says ignore van der Waals. OCR doesn't really like van der Waals for some reason. So down the group, your boiling point increases. Why? Because it must mean that this, more energy is needed to overcome the London forces because they're the only ones that are there, right? That must mean they're getting stronger. So then you need to think about why that's the case. What's changing? The only thing that's changing is that you're getting bigger down the group. There's more shells, right? So the reason is that there's more electrons down the group. Because the strength of London forces is determined by the number of electrons that there are as well. So if you're going down here, there's loads of electrons in iodine. It's like it's 53 compared to chlorine, which is 17. More electrons means you're going to have more induced dipole-dipole interactions, which means they're going to be stronger. Hydrogen iodide is decomposed into its elements. This is an endothermic reaction. It's much faster in a platinum catalyst. Complete the enthalpy profile diagram to show the formula of the reactants and products. Use EA to activate activation energy without EC for with, and then draw delta H to show the enthalpy change. So rather than memorizing the shape, just use your just think for a sec. This axis is enthalpy, right? So you can pick your reactants and you slap them here. So it's going to be 2HI gas. And it's an enthalpy change that is positive. So if it's a positive enthalpy change, it means it's going to go up anyway. So your products are going to be higher up. So rather than sitting and memorizing it, it's right there. I see so many people be like, I don't remember how to draw them. And I'm like, enthalpy change positive. It literally says enthalpy there. So your products are going to be more, right? So then what we need to do is we need to draw activation energy, which is energy required to get this reaction going, and then come back down again. So it's going to be like this. That's really badly drawn, right? And this is the activation energy from below here all the way to the peak. This is so badly drawn, but that's the activation energy, right? With a catalyst, the activation energy is less. So what's happening is that you've got like a less steep one here. So this is your activation energy with the catalyst, EC. The enthalpy change is the change that the enthalpy is going through. So it's going from the reactants to products like this. That's your enthalpy change because the enthalpy was here to start with and now it is here. So the change in their enthalpies, because this is a graph, is here. That's it. It's all right there for you. Now it says compound A is an oxide of chlorine and it's a liquid at room temperature and pressure and has a boiling point of that. When this much of A is heated to this gas is produced in the molecular formula. So we need to think about what's going on here. So we've got pressure, we've got a volume, we've got a mass. So we're thinking PV equals nRT. So PV equals nRT. What we're going to do, what links to the mass here, it's going to be the N. So N equals PV over RT. So that means it's going to be the pressure, so 1 times 10 to the 5 times its volume, which is 76, but we need in meters cubed. So to go from centimeters to meters, you would divide by 100. To go from a centimeter squared, you square this, you've got to divide this square, you've got to square that too. So then, from 1 centimeter cubed, you're going from 1 meter cubed, you're going to have to divide by this cubed, which means you're going to have to do 76 divided by a million. Or times 10 to the minus 6. That's the volume over 8.314 times its temperature, which they've told you is 100. So that's 273. So plus 100, so 373. If we do that, we get 2.45 times 10 to the minus 3 moles, right? But then they want to work on the molecular formula, so MR equals mass over moles, which is going to be 0.4485 over the moles of it, which is 2.45 times 10 to the minus 3. Which is 183. So then, some number of 35.5s and 16s gives you that. You can just muck about and eventually find it. It's Cl207. There you go, because you just add them up till it gets done. So there's only one way of doing these, and it's to read the question and follow it and actually use your brain and not just try and follow a routine, because routines do not work in these styles of questions, or it's a back titration or whatever you want to call it, reverse titration. It's literally all right there for you, dude. Like, you just gotta use it and read it. Compound B is an iodate in group 1. The iodate has this formula. Student carries out a titration to find the formula of this thing. So what they do is they dissolve 1.55 grams of B in 250 centimeters cubed, right? They then take 25 centimeters cubed of this, and then what do? They add 10 centimeters cubed of H2SO4, right? And whatever's in this, the iodate ions are reacting. So IO3 minus. Whenever you're doing these, think at each step, what is reacting with what and why? So that's that there. right? Then what they did is they then took this mixture, so that means this original mixture must have had IO3 minuses in them, right? And it's told you that as well. Then what they did is they took this resulting mixture, this whole shtick, and then they added Na2S2O3, right? And that's reacted with I2. So, and we know its concentration, so 0.10150 and its concentration, and this is the equation. So I always put a 1 and a 2 and remember it like that. And this is a mixture here that we've got from here. So look at these two together. So this step they took it and they added some acid and it made all of this. And then they took this mixture and then added this. So what's reacting with what? These two reacted to make I2. So all of the I2 must have reacted with this next thing here. So all of this I2 is that I2, which then you can work out to figure out how much of this IO3 minus there is, and you can work backward like that. So that's how you need to do that, or it just does not make sense. Like, no routines, no other way around it. It's reading comprehension. Now it says to complete the titrations, the titers, it's 24, 23.4, 23.75, 23.85. You just want to calculate it, that's fine. And then it says complete the table, work out the mean titer. So you're just going to pick the concordant results. So it's going to be the ones that are within 0.1 of each other, which are these two. So it's going to be 23.80. Then it says the uncertainty in each Buret reading is this. So what's the percentage uncertainty? And give your answer to two decimal places. So percentage uncertainty is going to be your uncertainty over your value, right? So what they did though is they did the initial reading and then the final reading. So they've done 2 times your uncertainty because they've done it twice, which is plus or minus 0.05 over the titration and titration 1, which is 24. So if we do that, we get 0.43% times 100, sorry. Then it says describe and explain how they could determine the endpoint of this titration accurately. So they're doing all of this blah blah blah, and then they're mixing it and titrating it with this, and then they're eventually making all of this stuff. So then what's happening here is we're making I2 and it's going to I minus. So the end product, the only way to know is to add starch, which reacts with iodine, not iodide, so it would go from blue to colorless, or blue-black if you want to, because it reacts with the iodine, but can you see how that iodine is becoming iodide? It's not the same thing, so it becomes colorless. Then it says determine the relative formula mass of this group 1 iodate. It's all right there because I've flowcharted it, now it makes sense. This titration, we need to figure out what these mean titer actually belongs to, what volume this is. This volume is here, 3.80. So now we can work that out, because I know if I can work out the moles of this, I know all of this I2 came from here, so I can find out how many moles came from here, and then eventually that and work back upwards. So then my moles of S2O32 minus, which would have come from the Na thing here, would have been its concentration times its volume, which is 0.150 times the mean titer, so 23.8 over 1,000. If I do that, we end up getting 3.57 times 10 to the minus 3 moles. Then I know that this is reacting only with the I2, which came from here. So the moles of the I2 is going to be a half of this, right? But then all of this must have come from here. So if there's 1 from here and there's now 3 here and then there's 1 here, this is the same as that 3. So that's the end of moles of I2 that was produced here that came here. That doesn't mean you have to times it up by 3 to get here. All of this became that. So if all of this became that, then that means the moles of I2 is a half of this. So then the moles of the IO3 minus is going to be a third of it. It's going to be 1/3 of this thing, because you can see this is 1 to 3. So that means you're going to half your answer, and then you're going to third the answer there as well, which would give you, so if I half it, so that's 3.57 times 10 to the minus 3, and then if I divide it by 2, and then I divide it by 3, you end up getting 5.95 times 10 to the minus 3 moles of this thing in 25 centimeters cubed, because remember, we actually took note of that. But remember, it came from a 250, so the moles of this IO3 minus in 250 is actually 10 times that, which is going to be 5.95 times 10 to the minus 2 moles instead. They've told us that they got 1.55 grams of this B and stuck it in this 250, and all of those IO3 minuses must have come from B. So that means the moles of this mysterious B is also the same as this. So then we can work out the MR of B by doing mass of a mole, which is 1.55 out. We get 260.5 grams per mole. The question's told you that this is an iodate which has IO3 minus in, so you can do 260.5 minus the MR of this IO3, and whatever's left over is going to be that. And if we do that, we get 260.5 minus 3 lots of 16, and then minus the iodine, which is what, 126.9? If we do that, we get 85.6, so it must have been, if you look at the periodic table, rubidium, which is 85.5. So the formula of B, you can't, so the relative mass of B, sorry, was 260.5, and the formula is to be RbIO3. You can't just put rubidium, you need to say what the actual formula of this thing is. This question's about some of the reactions of D-block elements and their ions, and here's the standard electropotentials. It says show the electron configuration of an Ni atom and then Ni2 plus ion. So a quick shortcut is that this is the S block, that's your D block, right, and that's your P whatever, right? This is period 1, 2, 3, 4. So what you can do is, if I know that this is magnesium, for example, that's 3, it's in the S block, so I know it's going to be 3S, and then it's the second one, 2. That's how I do that. In the D block, it's in period 4, but the only reason it's in period 4 is because they've got 4s and then 3D. Remember, the 4s fills first. So it's actually 3D. But then you can do the same thing here. 1, 2, 3, 4, 5, 6, 7, 8. So I know it's going to be 4s2, 3d8 for that one. I know. The only one that doesn't behave, the only two that don't behave that way is that this prefers to be 3d5 instead of 1, 2, 3, 4, 3d4. And that one prefers to be, copper prefers to be 3d10 instead of 3d9. But for the most part, every single other one is just 4s2, 3d8 and so forth. So here I know it's going to end in what 4s2, 3d8, so I just fill in the rest. So it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Now I always write the 4s first because it means I know and forcibly remember that it fills and empties first. So there's that. And then as well as that, the 4s empties and fills first. Sorry, fills and empties first. It's going to be 2s2, 2p6, 3s2, 3p6, 3d8. 4s is gone. There you go. Then it says a standard cell is set up with this cell below. So you got Ni solid and then this and this. And this is draw a label diagram to show how this could be used to sort out its cell potential. So we need to look at the half cells and we need to draw the rest. So we've got a half cell here, like a beaker, and we've got another beaker here. We need to figure out what solutions we're using. So we're going to use Ni and N2, and then it's a nickel solid, right? So we can use the nickel as the actual electrode here. So it's Ni solid, and then we're going to use 1 mole Dm minus 3 Ni2 plus aqueous solution, right? And if we look at the I minus, it's I2 aqueous to I2 minus aqueous. So because they're in the same phase, there's nothing we can use as an electrode other than platinum. All right. So then you've got I minus, I2 and I2 here, aqueous, and then 1 mole Dm as well. And then you've got to have the voltmeter here to actually measure this thing going on. But then this circuit's still not complete. A circuit needs to have a complete transfer of charge from one end to the other end, a constant loop of charge. So we need something to do that, and what we use is we put a salt bridge here instead. So salt bridge, and what happens is that like as the electrons move this way from here to here, this side, your positive ions like your K and your pluses, your NO3s will move from here to here to kind of keep the circuit going, continue the charge. And then as well as that, it says what's the standard conditions. So I've actually written it in there. I should have written 1 mole Dm minus 3 solutions, and the temperature is 298 kelvins, and there you go. Then it says predict the standard potential of this cell. So don't get tempted into jumping all like, oh, it must be oxidation reduction, like more negative this and that, blah, blah, blah. It's told you which one's doing what. So make sure you check the question. It hasn't already told you which way it's going first. Because you can see that's Ni to Ni2 plus. So that one's being oxidized. And then the I2 is being reduced, which obviously fits this here. But sometimes there have been questions where it's just kind of been the opposite. So for example, if you're recharging a cell, this would actually be reduced and that would be oxidized instead. So just be careful to not slip up on that. The E cell is whatever is E reduced minus the E ox. So that's going to be 0.54 minus 0.25, which means you're going to get 0.79 volts plus. Then it says use the information to help you arrive at the both parts of this question. So write the overall equation for the oxidation Fe2 plus and acidified H2O2. So if we're going to oxidize the Fe2 plus on our other side, we're going to end up with what? So let's have a quick look, shall we? So you need to look at whichever one has Fe2 plus and is being oxidized. So this one is being oxidized, and then it's told you what the acidified H2O2 is being reduced, right? So that means we're going to have this going this way, and then that one's going that way. There's 2 electrons here, and there's 2 there. So you balance it out, and you just cancel everything else that appears on both sides. If I just do that real quick, we get H2O2 aqueous plus 2H plus aqueous plus 2Fe2 plus aqueous goes to 2Fe3 plus aqueous plus H2O. Then it says zinc reacts readily with this to form this. Explain why this happens in terms of its electrode potentials and equilibria, and then include the equations for why this reactions occur. So if we look at what this is going on, it's saying zinc is a solid. It's going from it's going Zn to Zn2 plus. So where are you? So this one has to be oxidized. The question's told you that. And then it's told you it's reacted with acidified Cr2O72 minus to give you Cr2 plus. So we see here, we've got Cr2O72 minus, but that's not Cr2 plus. That's kind of weird. Why is that going on? Well, if you have a look, the question's told you that it's Cr2O72 minus and then it's Cr3 plus. So regardless, it's going to react with this, isn't it? And that's going to be reduced, right? But then you make Cr3 plus. Can you see Cr3 plus is there as well? And that becomes Cr2 plus. So you've now got a mixture with this in, but the zinc's still in there as well. This is more positive, so that's actually reduced as well. So what happens is, you get this oxidized, this is reduced, you make this, and then this gets reduced after as well, based on all of the things we just did. So we need to turn it into words, and then include overall equations for this. So what happens is that, have they numbered it? They haven't. Zn solid is oxidized because its E cell is more negative than So it's more negative than the CR20272 minus, which is reduced. Right? So let's write the equation for that. So the overall equation, again, if that's reduced, it's going that way, and if this one's being oxidized, it's going that way, and there's 2 electrons here, and there's 6 here, so we're going to times everything by 3 and cancel it out. So if I just quickly do that now, it would be 3Zn solid plus CR2072 minus aqueous plus 14H plus aqueous becomes 2 plus aqueous plus 2Cr3 plus aqueous plus 7H2O liquid. And it says acidified as well, and that's what the H plus is, and that fits with it, right? But then the Cr3 plus has an E cell that's more positive than Zn solid. So this becomes reduced, and that becomes oxidized. So then what happens is you're going this way, and then you're going this way. There's 2, and there's 1 there's 1 other way around. 1 and 2 in electrons, so we combine them, so we end up getting Zn solid plus 2Cr3 plus aqueous becomes Zn2 plus aqueous plus 2Cr minus 2 plus aqueous. And why does that happen? It's because we're saying that it shifts left. So what you would say in this case it's reduced because of whichever way around. So if we say oxidized, it would be where is it? Oxidized. So you'd also just add, sorry, in terms of equilibrium, it shifts left and right for the reduction and so forth. But there you go. So then it says 3 different reactions of copper compounds are described below. So they get aqueous copper sulfate, and they react with excess aqueous ammonia and ligand substitution. D blue solution is formed, and it's called this octahedral, and it's a trans isomer. Then it says here you got a hot dilute sulfuric acid disproportionation reaction, and you get a blue solution and a brown solid. And then it says copper 2 oxide is reacted with 1 dilute nitric acid and a neutralization reaction to form a blue solution. Unreacted copper 2 oxide is filtered off, and the real solution is left overnight in an evaporating basin, and you get this hydrated salt. And this is identify what CF are by their formula. So just step by step. The question's told you by formula or structure as appropriate. So C, what we've done is we've got aqueous copper sulfate, and we've added a lot of ammonia to get ligand substitution. When you add excess, what happens is 4 of those waters get swapped out. So the equation for C, well, the equation for C, I'll just write that, is H2O 6 2 plus some amount of NH3s aqueous gives you a partial substitution, and they've told you it's a trans isomer as well. So even hints at the fact that there's 4 waters and 2 of them have been swapped. So Cu H2O 2 NH3 4 2 plus aqueous plus the 4 H2Os that were booted off liquids, and then that means you're going to need 4 here. And its structure, and this is a trans isomer, so trans means it's on opposite sides, so it's going to be Cu, and if I just draw my wedges and all that stuff out, it gets a lot easier that way. So if it's trans, then the 2 waters are going to be on opposite sides, so H2O, and I always do lone pair by lone pair because that's easier to draw. And the other one's the NH3s, so NH3, NH3, H3N, and H3, like that. So that's that whole thing done. Cool. Now we need to look at what happens with D. So in D, what's going on is that we're reacting copper 1 oxide, so Cu2O is being reacted with this acid, and it's forming a disproportionation reaction. So then Cu2O plus H2SO4 is giving us what's going on here? Sorry, whoops. It's giving us a blue solution and a brown solid. So the blue solution must be CuSO4. The other brown solid must be, well, if you look at Cu2O, right, that's gone from +1 to +2, so that's been oxidized. If it's disproportionation, then the other copper here must have been reduced into Cu solid, and then what's left over is H2O, liquid. And then that's going to be aqueous, and that's and then as well as that, that's going to be aqueous. So then, in terms of, to show its disproportionation, Cu goes from +1 to +2 and +0, so it's disproportionation. So we figure that part out now as well. So we now know what D is and that is. We know we've got copper oxide, which is CuO, and they've added it with 1 dilute nitric acid and a neutralization reaction, so HNO3 aqueous as well, and that's 2 of them, and then you're going to get what? Some mysterious thing to form a blue solution, so it's going to be CuNO3 2 plus H2O, liquid, right? Cool. And then it says the untreated copper oxide is filtered off, and the solution is left overnight in evaporating basin, and then you get a hydrated salt. So it's going to be CuNO3.xH2O. So we need to figure what that out. So they've told us the percentages by mass of all of these things. So now you work out the ratios. So CuHNO. So that means it's going to be 26.29. That's going to be 2.48. That's going to be 11.59. That's going to be 5963. Right? So then we're going to divide it by 63.5, divide you by 1, divide you by 14, divide you by 16. Then this becomes, as a ratio, 0.414 2.48, and then it's going to be 11.5, 0.8278 or 9, and then that gives you 3.726, right? And then if we divide by the smallest number, we get 1. 2.48 divided by 0.414 gives us 5.99, and then if I do the next one, which is what was 0.8279, that gives us 1.999, and then if we do the 3.726, we get 9. So that means it's going to be 1 to 6 to 2 to 9. So then you just look at what you've got and then what's left over, and that should be it. So CU and no 3, 2, right? So that means we've dealt the CUs, we've got all those N's gone, and we've lost 6 of those. We have 3 O's left. So that means it's got to be 3H2O. That's it. And you can check with the atoms and they all add up. There you go. Thank you very much. I hope that helps. Please like, share, and subscribe, and you know the drill.